Well, how's everybody doing out there? Well, welcome to day 5 of Corona Online School. Hopefully, everybody had a great Labor Day weekend and stayed safe, but still had a lot of fun. So, today we're actually going to get into kind of the whole reason we were doing the set theory. So, if you were struggling with sections 2.1 and 2.2, I'm hoping this will seem a million times easier. And again, if we don't get 100% of the set theory stuff, like you'll see, like we're using a very minuscule amount of it for what we want to do kind of moving on. So keep working on it, keep practicing because it is good stuff. But keep asking questions. But again, don't get super stressed out about it if you're struggling with it a little bit. All right. So what we're going to look at is we're actually going to go into the addition and subtraction of whole numbers. So remember, whole numbers are the numbers that include 0 and all the counting numbers. So again, this is kind of getting into the arithmetic part of it. And so the very first kind of thing in green here is actually using the set theory model to actually introduce addition. So in this case, we're given two disjoint sets A and B. And so remember, they're disjoint because they don't have any kind of overlap or anything like that. They don't look like this. They don't have any kind of intersection or anything. This won't work if the sets overlap and they have intersection. So in this case, if you take the cardinality of A union B, it's the same thing as just taking the cardinality of A and adding it to the cardinality of B. And so in this case, if we assume little a is the cardinality of A and little b is the cardinality of B, then the above could also be written as A plus B equals the cardinality of A union B, where A and B are called add-ins or sum-ins. So again, the idea is we can actually use set theory as a way to talk about addition. So in this case, the number of elements that are in set A are 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 9 elements in set A, and we've got 1, 2, 3, 4, 5, 6 elements in set B. And again, since these are disjoint, to add these up, I just add the number in A plus the number in B, and then that gives me 15 total. So that set theory model is actually going to be one of the models that we use to talk about addition. So now remember, this wouldn't work if there was overlap or something like that, if we had overlapping intersections or anything like that. So again, this only works if it's disjoint, like we have here. All right, perfect. So now let's talk about some properties of addition. So these may look familiar. You may actually take them for granted and not realize like what they mean, because we do sort of take these things for granted every once in a while. But there's 4 properties of addition that we want to talk about. So there's the closure property, commutative property, associative property, and then the additive identity property of 0. So closure property, really what that means is if you take 2 whole numbers and add them together, then you're going to get another whole number. So the idea is I can't add like 1 plus 2 and get 4 thirds or something like that. I'm not going to get a fraction. So I'm always going to get a number that's also a whole number, is the idea. So that's kind of the main thing with that one. So again, if you add 2 whole numbers, you're always going to get a whole number as your answer. So commutative property just tells me I can add in any order. So for example, 7 plus 6 is 13, but so is 6 plus 7. So it doesn't matter which order I add them in, I'll always get the same answer. So that's our commutative property. Associative property means that if I have 3 numbers, I can add them in any order, and I'll still get the exact same answer. So if I had like 5 plus 3, so in this case, order of operations would tell me I have to add those parentheses first. So I'd get 2 plus 8 equals 10. But if I added it this way, so again, order of operations now tells me I had to add the 2 plus 5 first, which gives me 7, plus 3, which lo and behold equals 10. So again, you can rearrange, you can kind of move that parenthesis around and re-add, and you'll still end up with the same number. And then finally, additive identity property of 0 means if you add anything to 0, you always end up with the original thing back again. So like 2 plus 0 always equals 2. So it never changes what the answer is. All right, so let's look at example 1 real quick, and I'm hoping everybody yells out some answers here. So name the correct property that's demonstrated. So 7 plus 0 equals 7. Oh, I heard somebody say additive identity property of 0. Very good. I'm going to spell it right. Apparently I spelled it wrong in the packet. All right, so what about parentheses 6 plus 3 plus 2 equals 6 plus parentheses 3 plus 2? Oh, I think I heard somebody say it. Associative property. Very good. You guys are doing good at this. Nice. All right, 6 plus 3 equals 3 plus 6. Closure. Somebody say closure. No, it's commutative property. Commutative property. Very good. Good. And then finally, 2, 3, 4, 5 plus 6, 5, 4 is a whole number. So if I add those two whole numbers, I get a new whole number. So correct. Closure property is it. All right, very good. Good job. So again, we won't go into a lot of the details of these rules, but it doesn't hurt to keep them in the back of your mind. And like I said, recognize the difference between them and things like that. So, all right, so let's get into some of the addition properties or models of addition. So in this case, we're going to talk about two different models of addition. So set model, which was actually kind of demonstrated in that green box. That's basically what the set model looks like. And then the other one you might be familiar with is a measurement model, or kind of using a number line to add things up from there. So let's look at example 2. So I'm going to demonstrate each model, and then there'll be a bunch for you guys to practice. So Sam gives his friend Nancy 6 starburst and gives his friend Fred 5 starburst. How many starbursts did Sam give out? So in this case, again, this one's just kind of crying out for me for set model. And so what I'm going to do is I'm going to make one set that's for Nancy, and then one set that's for Fred. And so notice the way this is written, it doesn't say that Nancy and Fred are sharing any starburst or anything like that. So Nancy has her starburst, Fred has his starburst. There's no overlap, so that's why I drew the circles as two disjoint sets, so it looks like the picture above. And so in this case, Sam gave Nancy 6 starbursts. So let me draw little squares to represent my starburst here. So there's 6 for Nancy. I guess I should use different colors since starbursts come in all different colors. And then Fred, I'll use a different color for Fred. He had 5 starbursts. And so the goal is we want to know how many starbursts did Sam give out altogether. So again, in this case, what we're doing is we're thinking of this as that addition model. So we're really doing the union of N and F in this case. So what I'm going to do is I'm going to draw one big circle that has all the starbursts that Sam had in it originally. And so I'm going to add so there's Nancy's 6, and then to that I'm going to add Fred's 5, and then lo and behold, now I want to just kind of count them up. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it looks like Sam gave out 11 starburst to his friends. So again, I'm assuming you probably could have looked at this and just said 11 off the top of your head, but again, the point here is, yes, I want you to get the right answer, but we really want to focus on what the model actually looks like and making sure we actually demonstrate the proper model and things like that. So in this case, like I said, use different colors, use whatever it takes to kind of distinguish Nancy's pile from Fred's pile, but then show how they all kind of combine together, so that in the end, like what we've done is we basically pooled all their starburst and gotten one big pile to find out how many's there. So again, don't just write down 11. Like, that's not what I'm looking for. I'm looking for a demonstration of the model, because again, we're thinking of this not as you're learning it, but eventually you're going to be teaching this to other students, and how can we help them better understand the additions and things like that. So, all right. Any questions, just let me know. All right, so now what we've got is Julie walks 2 miles on Saturday and 5 miles on Sunday. How many total miles did she walk over the weekend? So anytime you're walking or anything like that, that one's just kind of crying out for a number line situation. And so what we're going to do is going to draw our little number line here. And so in this case, so remember we're using whole numbers, so we haven't learned what a negative number or anything that is, so we might as well just start right at 0. And then I'm going to give myself a little bit of room. I'm going to try to space it out a little bit here. And then if I need to, I can add some more. So in this case, we've got Julie walks 2 miles on Saturday and then 5 miles more on Sunday. How many total miles did she walk? So I'm going to let red be Saturday. So in this case, we're going to start at 0, and then we're going to jump 2 miles. So I'm going to put a little 2 up there to remind me how far we went. And then Sunday, I'm going to let represent, let's say, pink, say. And so then they walked 5 more miles on Sunday. So in this case, we got 1, 2, 3, 4, 5. So that means I want to jump to 7. And so the idea is wherever we land using the measurement model, that's going to be the total number of miles or the total number of things that we've done that day. So in this case, another way to think about it is we've got 2 miles the first day, 5 miles the second day for a total of 7. And if you want to, you can even draw a long jump that shows the overall. So this would be the overall 2 plus 5. But you don't have to. You can kind of just do the 2 jumps and leave it at that. So in this case, it looks like Julie walked 7 miles this weekend. So again, so those are the only 2 addition models that we're actually going to be using. So it's either the set model or the number line model. So again, if you have questions about that or anything, just let me know. Otherwise, let's get into the subtraction models. All right. So subtraction, so notice same thing. We're starting off again with kind of our set model to begin with. And so the difference is another word for subtraction. So this is the same thing as, so A minus B is the unique number C if and only if A equals B plus C. So basically they're almost thinking about it as a check in this case. So if I add B to C, it gives me back my A again. So in the equation, in this case, so remember in the addition one, A and B were both called add-ins or sum-ins, so they were interchangeable, so you could use them either way. For subtraction, each part has its own name. So in this case, the A part is what's called the minuend. So the first part is a subtraction, and the part that's being subtracted is the subtrahend. And then C itself is just called the difference between those two. So again, just like addition, we can use our set model to represent this. So in this case, again, just like before, set A had 9 elements in it. Set B had 6 elements in it. But in this case, since they're disjoint, again, we can add or subtract them. In this case, we're trying to subtract them, so A minus B would just be 3 in this case. So what we want to do is actually kind of use this idea to demonstrate using 4 different models. So takeaway, missing add-in, comparison, and measurement number line in this case. All right, so again, we want to focus on the techniques, not necessarily just what the answer is, because again, I'm sure you can just shout out what the answer is, but we want to focus on how we'd actually get these answers and things like that. So the takeaway method is kind of like the set theory method, But instead of like adding stuff to a pile, we're going to take things away. So in this case, John has 7 candies. His brother takes 2 candies from him. How many does John have left? So what we want to do is start off with, whoops, pen's not working for some reason. Oh, hold on. What in the world? It was just working a second ago. What's wrong? All right, if you want to go get a drink or take a TV timeout, feel free. Well, this is... There we go. All right, we're back. So, in this case, this one's kind of crying out for the takeaway method. And so what we've got is John has his 7 candies. So I'm just going to sketch 7 candies here. So again, you can use different colors. You can draw the candies however you want. Again, we're focused on the model, not again what the solution is as much. Let's see, 1, 2, 3, 4, 5, 6. So there's John's 7 candies that he has. And the idea is his brother takes 2 candies away from him. So his brothers are going to take 2 candies, and they're going to go away. They're going to eat them, whatever it takes. So the idea is we're taking them away from this pile. And how many candies does John have left over? So what he has left over are these guys here. So it'd be 1, 2, 3, 4, 5. So John has 5 candies left. So again, I drew all the candies, took the 2 away that his brother took, and then whatever he had left over was how much he had remaining. Perfect. All right. So in this case, example 5, Bill has $4. He needs $6 for lunch. How much more money does Bill need for lunch? So this one is a little tricky, but this is what's called the missing add-in. Because even though it's technically a subtraction problem, it's kind of written as an algebra problem. So you don't have to write, I mean, you can write this for your own notes, but you wouldn't write this for students or anything like that. But basically, it's kind of set up like a little algebraic equation like that, because we know how much Bill has to start with, and we know how much he wants. So that's why it's the missing add-in, because the problem is we need to figure out what that number is that add to 4 that'll take us up to 6. In this case. So the way I usually draw these is almost again kind of like a set model. So in this case, I'll say, okay, here's the money that Bill currently has. And then I know this is how much Bill needs. So this is how much lunch is. This is how much Bill needs. So the goal is I want to make the circle on the left look like the circle on the right. So how many more dollar bills do I have to put into the circle on the left? So in this case, if I wanted to match up, I would need to put 2 more dollar signs. So in this case, it looks like Bill needs 2 more dollars to be able to afford lunch in this case. And so again, notice I used different colors so I could distinguish what he had from what he needed. So in this case, Bill needs 2 more dollars to get lunch. All right. So again, both of these kind of look like similar to set theory, but again, the difference is on the first one, it was written kind of as a true subtraction. It was basically 7 minus 2 equals 5. Where this one was written more like 4 plus x equals 6. So kind of see the subtle difference between these subtraction problems. All right, so let's look at comparison here. So example 6. So Sue has $7. Ann has $6. How many more dollars does Sue have than Ann? So again, this one's crying out for comparison because you've got two similar things that you're trying to compare to see the difference between them. So again, let me draw some dolls here. So these are going to be Sue's dolls up top. So you guys didn't know you were signed up for art class, did you? Look at how beautiful this art is. It's crazy. 2, 3, 4, 5, 6. And you wonder why I went into math. And then let's draw Anne's dolls in, say, blue. So Anne had 6 dolls. Oops. And so notice I tried to make them so they actually lined up and things like that, so it makes it a little bit easier. And then the goal is we want to know how many more dolls does Sue have than Anne. So the reason I drew them this way is so I could kind of just match them up and say, well, they match dolls there, 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 and they match dolls there. So these are the ones that they have in common. But when I get down to the end, or if there were a bunch more at the end, anything that's left over would be the ones that Sue has more. So in this case, it's just one. So Sue just has one more doll than Anne. So Sue has... And so again, so I try to keep my diagrams real neat and stuff like that. And so again, I didn't write any kind of subtraction problem. If you were to write one, this one would look like 7 minus 6 equals 1 in this case. But again, I want you to focus more on the model, not necessarily the equations at the moment. And then finally, example 7, John walked 5 miles to school. 2 miles were walked after he picked up Sam at his house. How many miles did John walk before he picked up Sam? So again, since we're walking, this is going to be another measurement model. So just like, or number line, however you want to call it. So I'll call it number line. And so again, just like before, since we're dealing with whole numbers, I'm just going to start with 0 on the left and then count up. So 1, 2, 3, 4, 5, 6. And if I need more room, I can always add more on. So in this case, they told us how far John walked to school. So John walked 5 miles to school. So in this case, so maybe this was John's home over here, maybe, who knows. And then school is over here. So John walked 5 miles, so we want to draw one big arrow that takes you to 5. And so now 2 miles were walked after he picked up Sam. So at some point in time, he picked up Sam and walked the last 2 miles to school with Sam. Now this, you want to be a little careful. Some books do it some ways. I'm kind of torn. I can go either way. Some, depending on how you've learned this in the past, like what you may have done is you may have started where the 5 was and drawn your arrow this way. And I'm totally good with that because it kind of tells you which way you're going. Some other books, unfortunately, you'll see where they have you draw it this way. Oops, I lost the whole line. Hold on. They'll have you where the arrows meet up because it's a subtraction. So I don't know if people have seen it that way or not. I may ask everybody a poll and see if they remember. So I'm fine kind of with either way. I know some books are really particular about subtractions. The 2 arrowheads always have to meet. Additions, like the tail and the arrow always meet. For me, like I said, I can go either way. I mean, it doesn't bother me to see... Oops, I've erased everything again. It doesn't bother me to see an arrow there and then a jump of 2 backwards, because that also tells me that it was a subtraction. So in this case, because I can think of that as a movement of -2. So I may ask everybody and see if they have a preference or anything like that, or if they even remember when they were doing this, if they had a preference and stuff like that. So if you draw the backwards arrow like I drew there, that's totally good with me. If you want to draw the 2 arrows that meet, That's fine with me also. I'm not going to be too picky about it as long as we're actually getting them correct, because I can tell which one's addition and which one's subtraction. So in this case, this must have been, what we're saying is this, again, just like on the addition one, this will be our answer. So this must have been where Sam's house was, like 2 miles from the school. So Sam's house was 2 miles from the school. And so this is how far John walked by himself. So this is John. So in this case, John walked, whoops. Three miles by himself. All right. So this gives you kind of a sample of every possible scenario out there. So again, just to kind of summarize, so for addition, we had our set model, which is to basically just draw a big picture with circles around them. Think of them as sets and stuff like that. Example 3, we had our number line. That again, just regular old number line. Example 4 was again kind of a set model where we took some stuff away. So in this case, I kind of pulled the 2 candies out. Whatever was left over in the set was what the answer was. Our missing addend, again, so we kind of know part of the addition. We know the answer. We just don't know what happens in the middle. And so we have to figure out what that is. Comparison model, again, just kind of draw pictures of similar things and just compare the two. And then again, another number line model. So if you have any questions, I'm hoping this seems like a million times easier than 2.1 and 2.2. And again, this is more what I'm worried about. I mean, I'm not saying there won't be a little bit of set theory and stuff like that on the test, and it shouldn't keep practicing it and stuff like that. But this is going to be more along the lines of what we're teaching. And the reason we talked about set theory was actually just kind of that addition and subtraction rule and how we can use it for arithmetic, not necessarily some of the really tougher parts of it. But feel free to ask questions. I'm here to help you guys. I'm glad everybody's back from Labor Day. Hope everybody had a good time, and I'll be around the computer all day if you have any questions.